Ever feel like you're just wading through tons of information, trying to get a handle on a new design idea or maybe some tech concept?
Yeah, or you just wish you could find a way to quickly grasp the really important stuff, without spending days on it.
Exactly. And that's what we're aiming for here.
Welcome. This is the deep dive. We try to give you that informed edge. We take a focused look at different sources, pull out the key insights,
Surprising bits, the connections.
and those moments where it just clicks, all aimed at you, the person who really wants to learn and understand.
So today we're digging into something pretty interesting. It's an excerpt from a lecture video called 2025 Data in Design Class, O2 Lecture Programming and Data Processing 1.mp4.
Right. Think of this as your, let's say, faster route to understanding how programming data and design thinking connect, at least according to this lecture.
Yeah, our mission, if you will, is to really break down the core ideas from this session. What do they actually mean for designers?
And I'm here to help guide us through it, make sure we, pull out the most valuable bits of knowledge.
Okay, so let's jump in. The first big concept that jumps out from the lecture is this idea that all software is essentially a data processor, whether it's your map app or complex CAD software.
That's fundamental. The lecturer really nails it down. They say, basically, software is a data processor. Yeah, so need input and do whatever they want behind the scene, and it will return the outcome value on the screen or on our side, right, so that we can understand what is the result out of this data process.
So simple, really. Input, process, output,
Pretty much. It takes stuff in, does its thing based on instructions, and gives you something back.
which, immediately makes me think, as a designer,
Yeah.
how do we start seeing our own ideas, our concepts, as a form of data?
Ah, that's the key shift, isn't it? If you can frame your design thinking like a shape or a relationship between spaces, or even how someone might interact with something if you frame that as data.
Then you can use computation to explore it.
Exactly. Explore variations, test performance, maybe even generate things you hadn't thought of. But it does mean you need to be, well, a bit more structured in how you define things.
And structure brings us right to the next point,
Yep.
the building blocks. Data types and data structures. Sounds technical, maybe, but the lecture insists this is crucial stuff.
Oh, absolutely vital, because you need to tell the computer precisely what kind of information you're giving it. The lecture highlights this. There's a quote. So the data type is basically really important because it talks about basically connecting between the data and user and the computer to compute.
Connecting the dots, basically.
Right. Is it a whole number, an integer, a number with decimals, a float? Is it text, a string, or maybe a category like wood or steel?
Or numerical discrete, like counting items, versus continuous, like measuring a length.
Yes, all those distinctions. It's like giving the computer the right vocabulary, so it understands the kind of information it's dealing with.
Okay, that makes sense. And then data structures. That's how you organize this data.
Precisely. It's how you arrange those individual pieces of data. The lecture mentions a few common ones. Lists, like a shopping list, just ordered items. Linked lists, where each item points to the next one. Stacks. Think of a pile of plates, right? The last one on is the first one off. LIFO, last in, first out.
Like the CD case analogy they used.
Exactly like that. And then queues, which are like waiting in line, first in, first out, or FIFO.
Got it.
And there are others like graphs for networks, hash tables, or dictionaries for quick lookups using a key.
And the important thing the lecture stresses is
Yeah.
that the designer should be choosing these based on their concept, not just, copying some code.
Yes, that was key quote.
Yeah.
The designer need to describe the data structure based on their concept or their problem. So this is, I think, really important concept. Otherwise, you just copy other code.
Right. Understand why you're using a list versus a stack, for example.
Because it affects how efficiently you can represent and work with your design information. If you're dealing with hierarchy, maybe a tree structure. If it's steps in a process, maybe a key makes sense.
This all seems to feed into this broader idea of computational thinking, which the lecture also brings up. It's presented as a way to approach design problems, but it's not just about coding, is it?
Not at all. It's more a problem-solving mindset, borrowing ideas from computer science. The lecture breaks it down into 4 main parts.
Okay.
Decomposition, breaking big problems into smaller ones. Pattern recognition, seeing similarities or recurring themes.
Right.
Abstraction,
Yeah.
focusing only on the essential details, ignoring the noise. And finally, algorithm design, creating that step-by-step plan to get to a solution.
They used that great example, didn't they? Explaining how to make a peanut butter and jelly sandwich.
Yeah, it highlights how much we humans just assume. We have all this implicit knowledge.
But a computer needs every single tiny step spelled out. Open the jar, pick up the knife.
Exactly. Computational thinking forces you to make everything explicit, logical. There's another quote on this. So I guess the most important concept of computation design is to apply computation thinking for the design process. I think that sentence is correct to me.
Applying that structured thinking to design.
Yeah. Taking that logical approach into a field that's often, well, more intuitive. Think about designing modular furniture. Decomposition breaks it into parts. Patterns are the connections. Abstraction is the core function. The algorithm is the assembly rules.
Which brings us to another really key phrase from the lecture. Shifting from implicit to explicit design processes. That sounds fundamental.
It really is. Traditional design can rely a lot on gut feeling, experience, stuff that's hard to pin down, that's the implicit.
Right.
Computational design demands you make it all explicit. Every step, every decision, defined clearly enough for a computer to follow. The lecturer says, the most important thing in computational design is changing from implicit design process to explicit design process.
And making it explicit allows for automation, maybe. More precision.
Definitely. And also makes it easier to share, to reproduce. If an architect adjusts a facade detail by eye implicitly, that's hard to replicate. If it's based on explicit rules, parameters, anyone can follow it.
Okay, so to actually do this, you need tools. The lecture mentions software like Rhino and programming languages. Python gets an indirect mention via RhinoScript, Rhino Common, and APIs. What are APIs exactly?
Right. So think of Rhino as this powerful workshop, full of tools for making shapes and stuff. An API, an application programming interface, is like a controlled way to use those tools from the outside, maybe in your own custom script or process.
So you don't need to know how Rhino built the tool, just how to ask for it.
Exactly. The lecturer used an analogy like a software company protecting its secret sauce, its valuable code, but letting you use the features through this interface. Like ordering off a restaurant menu, you use the menu, the API, to get what you want without needing to go in the kitchen.
Makes sense. So RhinoScript and Rhino Common are like specific menus for Rhino.
Precisely. They let designers write scripts to automate tasks or create custom tools within Rhino, using its built-in power without rewriting everything from scratch. You could script facade variations based on sun data, for instance.
Gotcha. Now, something else mentioned was spatial data, projections, coordinate systems. Why is defining space so critical here?
Well, because so much design is about space and form, right? And computationally, you need absolute precision. You define space using coordinate systems.
Like XYZ.
Like XYZ. But the lecture points out that the same point can mean different things depending on the system or projection. Think about a point on a curved surface.
Okay.
You can describe it with its XYZ coordinates in 3D space, but you could also describe it with UV coordinates, which relate to its position on the flattened 2D version of that surface.
Ah, okay. Like unwrapping the surface.
Exactly. And knowing when to use which system, XYZ for the overall model, maybe UV for manufacturing instructions, is fundamental to getting the geometry right.
So with all this precision needed, mistakes must happen. Bugs. Debugging seems like a big deal in the lecture.
Oh, it's unavoidable, part of the process. Bugs are just errors in the code or logic.
Right.
The lecture mentions different kinds. Syntax errors, like typos in the code, runtime errors, where it crashes while running, and semantic errors, the trickiest ones, where it runs fine but does the wrong thing.
Doesn't give you the result you expected?
Precisely. And that anecdote they shared about the senior engineer taking a month and a half to find one bug.
Wow. That really drives it home.
It shows how complex debugging can be. It's like finding a tiny flaw in a huge, intricate machine.
It sounds like detective work. And they mentioned that counterintuitive idea, the first rule of debugging. Do nothing. What's that about?
It's about resisting that immediate panic, the urge to just start changing things randomly, hoping it fixes the problem.
Yeah, I've done that.
We all have. But the idea is stop. Understand the problem first. Find the root cause, not just the symptom. Like treating a cough, the cough's the symptom. You need to find the underlying illness.
Makes sense. Don't just patch over the crack. Find out why the wall is cracking.
Exactly. And they mentioned rubber duck debugging.
Oh, yeah. Explain your code line by line to a rubber duck.
Sounds silly, but honestly, just the act of articulating your logic out loud often makes you spot the flaw yourself. You become your own debugger.
Clever. Okay. Shifting gears slightly, the lecture also touched on different design paradigms, agent-based, parametric, generative, procedural. How do these fit in?
These are like different strategies or philosophies for designing. Agent-based uses little autonomous things interacting. Parametric is all about relationships and adjustable
Right, like
parameters.
sliders controlling a shape.
Yeah. Generative uses algorithms to explore lots of options based on goals. Procedural defines a set sequence of steps.
And these link to programming approaches.
They often do. Agent-based might suit object-oriented programming. Parametric relies heavily on functions and variables. But the core message, quoting the lecture again, is that computation design is a process, application of computation thinking.
So it's the process that matters most, not just which fancy technique you use.
Exactly. It's not necessarily about making crazy complex shapes, though you can. It's about applying that computational mindset, whatever the specific design approach is.
Okay. Then there's this idea about information resolution, precision of information. How does that connect?
Well, think about how clearly information is conveyed. Spoken language can be ambiguous, right? Written text is usually clearer. But mathematical or logical systems, they aim for total precision.
No room for misinterpretation.
Ideally, yes. And computers need that precision. The lecture emphasized math's role, saying math is basically basic language for every domains like chemistry, business engineering, architecture, design, whatever.
Because it's unambiguous.
Right. So translating design ideas for a computer forces you towards that higher resolution, that logical clarity. It pushes the design process itself to be more explainable.
And being clear about the process helps avoid just treating the computer like a black box.
Right.
Right, which the lecture warned about.
Absolutely. The black box danger is taking the output, some cool image or model, without understanding how it got there. What data went in, what algorithm was
The
used.
garbage in, garbage out principle.
Exactly that. If the input data is bad or the algorithm is flawed, the output might look impressive but be totally meaningless. You can't just rely on, interpreting the pretty pictures without understanding the engine underneath.
You need that critical engagement with the whole process.
Definitely.
So, thinking practically,
Mm-hmm.
how does this apply in, say, a design competition or a studio project? Is it just theory?
No, very practical. The lecture stresses it's a process you can apply at different stages. You don't have to automate everything.
So you could use computational thinking just to break down the problem.
Sure. Or develop a small algorithm to optimize one specific aspect, like material use. Or use a parametric model to quickly explore variations of a particular detail.
So it's about strategically using these tools and ways of thinking.
Exactly. Leveraging them to enhance your design work, explore things you couldn't easily do manually. It's a tool set and a mindset.
Okay, so if we boil it all down, the main takeaway from this lecture seems to be computational design isn't just about the code or the software itself.
Right. It's fundamentally about applying that computational thinking to how you design, focusing on data, making things explicit, solving problems logically.
And understanding this, even at a foundational level, can really change how you approach design challenges, right? It gives you a new perspective, a way to use these tools more powerfully.
It really can. Think about it. How might understanding data structures change how you organize elements in your next project? Could you take something you normally do implicitly, intuitively, and try to make it explicit? Define the steps.
That's a really interesting challenge. What hidden rules am I following that I could actually spell out?
Exactly. It forces a different kind of reflection.
Definitely food for thought.
Mm.
So if this has sparked your interest, maybe look into data types, data structures, computational thinking a bit more.
Yeah, there are great resources out there. Even playing with visual programming tools can give you a feel for it without diving deep into code straight away.
Get your hands dirty a little bit.
It's often the best way to learn.
Well, great insights today. Lots to think about.
Absolutely. Until our next depth dive, keep exploring those connections. Design, data, computation. It's a fascinating intersection.
Thanks for joining us.